Can everyone see the screen?
Yes.
Maybe can. Yeah. Okay. Great. Great. Thank you. So, so in the interest of time, I'm just going to start right away. I'm going to go into full screen mode. And so I've prepared this deck and I'll talk through it. We'll go fairly slowly. Um, I'll cover some of these things later, the pace and so on. But this is mainly for people who are not, actually, this is only for people who are not AI/ML experts. So, um, so I'll start with an executive summary of what we're going to talk about over the next two or maybe three sessions. Just sort of very high level takeaway points. So the first thing I want people to understand is AI is not magic. This is something that people outside the organization may tell us, but this should not be our perspective of AI. It's far from magic. All it is, as we will see in this session as well as in subsequent sessions, it is an extension of standard correlation analysis. Right? It's just a sophisticated way of discovering correlations in data. In order to predict something from the data, there's two things that AI needs. It needs lots of examples to learn a correlation from, and these examples are called training data. Again, we'll encounter all of these concepts later, so don't worry. And the second thing it needs is, in the data, there has to be a signal about the outcome you want to predict. So whatever outcome you're looking for from the AI, the data should have a signal for that outcome. If it doesn't have a signal, you can't do it. Right? So that's all AI is really when it comes down to it. Don't believe any of the hype that you hear in the news or in sort of popular media or popular articles and so on. Right? It's just that it's hype. The second point I want all of us to come away with is the more signal you have about the outcome from the data, the better. And I completely understand this is going to sound a bit wishy-washy to you. And all of these concepts will sort of get clear as we go through the lecture. So the more signal you have about the outcome you want to predict, the better it is. And the more good quality data you have, the better it is. Usually quality trumps quantity. And having good annotation, again, all of this is going to be defined later, is part of good quality. The third part, very important for all of us outside AI to understand, is that development of AI software or development of an AI solution is very, very sensitive to the type and the value of the accuracy metric you want to optimize. Now, this may sound abstract at this point, but just keep this in your mind. This is going to be an important point later. And because of this, it's important to identify what accuracy are you aiming for, what is the metric you're aiming for, and what is going to be the numerical value of the metric upfront. This is not always possible, but it's important to have it in the back of your mind. The last point I want us to come away with is that evaluation and iteration after deployment are fundamental to AI. You can't escape this. AI is not a piece of software that you can just deploy and forget about. It's only as good as the data that went into it, and therefore, as the characteristics of this data change with time, the AI needs to be redeveloped and retrained with more data, with fresh data, new data, and so on. So this is sort of an executive summary. There's a lot of detail hidden in these 4 points, which is what we'll uncover through the next three sessions, 2 or 3 sessions. Right? And yeah, so that's the outline. We're going to cover 5 things. First is how very high level view of how AI works. The second is data and everything that has to do with data. The third is how you evaluate an AI model. The fourth is what are the things you need to worry about when you deploy an AI model? What does AI in deployment look like? And the fifth is, given all of these things, how are we going to work in this institute in order to be successful? So I expect that in this session today, we'll just cover the first 2 points, namely how AI works and all of the aspects around data. And the remaining points will be covered in the following session or maybe even 2 more sessions. We'll see how it goes. So before I start, there's some ground rules. The first is there is a significant amount of material I'm going to cover. For a lot of people in this audience, this material is going to be new. A lot of us here don't have exposure to AI, but we work in an institute whose sort of core language or core medium is AI. So I'm going to repeat a lot of material, and some of you may get bored, but it's okay. Just bear with me. For the rest of you who are not bored, and if things are going over your head, please feel free to interrupt. Feel free to ask me to slow down, to repeat a point again. I have I have absolutely no problem in doing so. So at this stage, while we are going through this, there is no stupid question. You can ask any question you like. There is no judgment. There is no stupid question at all. What I really want is that all of us understand what we are doing. Yeah. So each one of you should understand the material really well. And later, we don't want excuses. We don't want that 6 months down the road, people come back and say, "Oh, I don't know what's a data split" or something like that, right? So we'll do this presentation this time. We'll take feedback. I'll iterate the material. I'll refine it. I'm going to do it a lot of times with new people who come in. I'm going to do an onboarding thing, perhaps even once a month, where I'll be using this material. So this material will continue to be refined. We're going to record it. It will be available for people to review. We really don't want there to be any excuses later, right? And the reason is that as an AI organization, we really should be able to explain AI at the level that is covered in this material to the external world. For things that are covered in this material, we don't need to bring somebody from the AI/ML team into a meeting. It shouldn't be necessary. Any of us should be able to talk this language, participate in external discussions. That's the first goal. The second goal is internally, we want to be able to engage fruitfully with the AI/ML team. It shouldn't sound like Greek, right? What the AI/ML team says, I know this from experience. To a lot of people, it sounds like Greek. So they consider it an isolated entity. They consider AI/ML to be a black box that, let's just take what they say as gospel truth. Let's not question it. And let's just blindly transmit information from there to the external world. That's not, we won't be successful that way. We have to be able to question each other. We have to be able to ask the right questions, and we have to be able to set concrete and informed targets for the AI/ML team. And targets doesn't mean something that is completely unreasonable, that I want 100% accuracy on everything. For example, they have to be informed targets, right? And in order to set informed targets, you need to understand what AI is. The third point is, I'm reiterating something I've said before. None of us after this training should call AI work magic, right? That word is sort of, that word should disappear from our vocabulary. That will be the position of people that we engage with, but we should be able to dispel that, right? And the training that I'm giving you here, it's not comprehensive, right? It's not like as if doing 3 sessions of AI training is going to suddenly make you an AI expert. It's not going to happen, right? It is simplified, right? And all of you are from different domains. You're experts in your own domains. And you know that whenever you try to simplify a certain domain, and AI/ML is not an exception to this, this is true of any domain, every simplification loses an element of the truth. You try to simplify and explain something, you will gloss over something else. That's in some sense, that's also the purpose of simplification, is to extract the essential elements and only convey those. But when you convey the essential elements, you avoid certain things, you avoid certain nuanced discussions. So because of that, you will find exceptions to what I state here. I'll try and point out exceptions along the way, but there will be exceptions. I'll make certain blanket statements to which there are a few exceptions. So you'll encounter exceptions. And eventually you should be able to think about the exceptions in the context of the general rule. So it's the exceptions proving the rule in a sense. Right? So you should be able to think about these exceptions in a nuanced way. You should be able to participate in discussions and use this training as sort of your background context. Everything else is sort of a ripple on top of this lake, if you will. And the ripples destroy the flatness of the lake. Right? And when you start seeing the ripples, that's the first step towards becoming an expert. Again, feel free to interrupt at any point. I am not sure I'll be able to see raised hands because um, I'm in the sort of middle of the deck. But if somebody can volunteer to keep track of raised hands, maybe Joanna, if you can just let me know if somebody is raising a hand and wants to ask a
Sure,
question,
sure.
just interrupt me. What will I not talk about in this? I'm not going to talk about AI algorithms for the most part. There'll be some very tangential um, comments about AI algorithms, some jargon that I will introduce because it's jargon that's used fairly often. So in a very high level manner, I may talk about AI algorithms, but for the large part, I'm not going to discuss AI algorithms. And that's because AI algorithms are the domain of the AIML team. And it's not really necessary for us here to know how to solve a problem that is stated as an AI problem, right? We need to know how to get there, and we need to know what comes out of an AI problem, but we don't need to know how to solve it as an AI problem. Now, those of you who are technically inclined, there's additional course material on the web and so on. You can of course pick up AI algorithms from if you're curious. But for all of you here, for the most part, it's not necessary for the job, right? So, what is necessary for the job? What am I trying to address here? So these are the various bullet points, right? First, what you should understand at a broad level, at a high level, what is AI and what it isn't. You need to understand when AI is needed, whether it's worth building an AI model in a certain context in the first place. There are many cases, in fact, most cases, it's simply not worth building an AI model. We shouldn't start jumping up and down just because we are an AI institute and start saying that, oh, this problem is solvable with AI and that problem is solvable. Problems are not solvable with AI. We will address a very niche set of problems where AI actually makes sense. So that's the second part. The third is, how does data link to AI? Data is integral to AI. So how does data input into AI? How does data come out? How much data is needed? What aspects of the data are important? You should have a high level understanding of this. Um, Fourth, understanding basic analysis one performs on data. And I'll give you examples of this type of very basic analysis, something that's accessible to everybody. Next is understanding means of diagnosing, when AI models go wrong, what are the tools you have available at hand to diagnose problems with AI models? Again, this is largely in the purview of the AIML team to diagnose problems. But again, I think it's very important that all of us have a high level understanding of this. There's some very simple things that you can have, simple constructs that will help in diagnosing problems with AI models. The next is understanding how to evaluate them. And this is a very, very important part, right? How do you evaluate an AI model? How good is it? Depending on the context. Again, evaluation always depends on the context. What kind of model is it? For what application has it been built? Where are you deploying it? In what kind of environment? How is it being used? Is there a human involved? Is there no human involved? All of these matters are important in understanding how to evaluate AI models. Next, understanding what is expected to happen when AI models are deployed, what the pitfalls are, when do AI models need to be retrained or reversioned, right? And after we understand all this should flow into what we are as an institute, how we as an institute should work. Yeah, is it clear? So I'll pause here if there are any questions before we get into the meat of the session. No questions?
Help, this is JK.
Yes.
Can you
Yes,
please
JK.
dive a little bit more on how much data is adequate?
Yeah. We'll talk about it. We'll
Okay.
talk about it. So, yeah. And that's one of the questions. There's no hard and fast answer, but there's some sort of thumb rules that I'll talk about. Any other questions?
I think just one thing. We often hear and use ourselves AI and ML interchangeably. So
Yes.
maybe just the difference between the two also, if you could comment.
Okay. Yeah, that's a good question. I haven't directly addressed that in the deck. As far as we are concerned, they're interchangeable. Some people distinguish ML from DL. So ML is basically um, machine learning before the advent of deep learning, whereas DL is using neural network models to analyze data. And ML and DL taken together constitutes modern AI. Now, if you really want to sort of split hairs, AI is larger than just learning, right? So ML, machine learning, DL, deep learning, taken together is learning from data. There can be some forms of designing intelligent systems that go beyond learning. I don't really want to get into that. Most of what constitutes AI today is learning systems. And learning systems are of two types, either classical machine learning models or deep learning models.
Got it. Thanks.
Does that help?
Yeah, it does.
Yeah. Okay. Okay, so let's start. What is AI? As we commonly use it in today's world, as it is commonly used or applied, AI is not a machine or program that thinks. Right? So it's not contrary to the name, it's not a thinking machine. It's not intelligent. It's not some piece of code that mysteriously acquires a certain intelligence. All it does is it finds complex correlations within the data. So it gives the illusion of an entity that thinks. Okay, very important to understand this. So very simple example. Suppose you have a toddler that's given ice cream every day just before sunset. So after a few days, the toddler will correlate ice cream and sunset. Right? She will expect the sun to set whenever she's given ice cream. Now, she's not thinking. She doesn't know how to tell the time, but she's seen a pattern. So she knows how to do correlation. She knows how to say, okay, when A happens, B always happens. She doesn't really know how to tell the time. So she's only exploiting a correlation discovered through historical experience. Right? So she will expect, after a few days of this, she's going to expect the sun to set whenever she's given ice cream. She'll look out of the window and check, has the sun set? Because she knows about this correlation. This, in a nutshell, is exactly what AI does. It's as simple as this, in some sense. Right? So what are some examples from the work that we do? There are correlations between certain factors that the AI has identified and the risk of a disease outcome. Right? And the AI discovers this correlation. So it says, well, when these factors are present, or when these factors take certain numerical values, you're very likely to get this disease. If your cough sound has this pattern, you're very likely to have TB. And why does it know this? Because it has seen these correlations. It's exploited correlations between the patterns in the cough sounds and the disease outcome. Similarly, it correlates certain patterns in a baby picture to the baby weight or the height. You show enough examples. It's just like the toddler learning from examples of ice cream and sunset and learning that correlation. You show it enough examples, it learns to correlate. Oh, there is this weird aspect in the baby picture that's correlated with the weight value or the height value. And it learns to exploit that. So the next time you show it a baby picture, it's going to say, aha, I've seen this pattern before, and I know this is associated with that weight value. So I'm going to predict that weight value for the baby. For our pest management solution, the AI sees, or the algorithm sees some shape on a piece of paper and says, this is a pest. How does it know it's a pest? Because it's seen a lot of examples of this, where we force it to call it a pest. We say, okay, when you see something like this, when you see a shape like this, it's a pink bollworm or an American worm. Right? So it's exploiting these correlations. So an AI algorithm, which is what the AI ML experts develop, finds
Alpan,
this correlation. Yes.
hi. Alpan, this is Shekhar. Alpan,
Hi,
so,
Shekhar.
hi. These correlations, just for me to understand, these are all resident in the domain.
Yes.
So they're not
What do you mean?
resident.
What do
They're
you mean
not,
resident in
in
the
other
domain?
words, the entire aspect of uncovering these factors tend to be very strongly resident in the subject matter that we are studying. So we may not be able to hear an engine sound unless you're a trained person to understand at what level
Yeah.
does it demonstrate malfunction, whereas a trained engineer can, or a Neeraj can even on a human level detect because he's a trained person in the
Yes.
field of
Yes,
what
I
he
will
does.
come to that. There's some subtleties to that. When can a human or an expert human uh, detect the correlation? When can they not? What type of AI is that? I'll come to that a little bit later, a couple of slides down.
Understood. But is it fair to say that AI/ML folks blandly will find it difficult to find these correlations? They have to be led with the domain team to even start the discovery process, right? In other words,
Yes, well,
this does require somebody who is either a doctor, an etymologist, a pest management expert.
not always. Not always. Again, I'll talk about that. Not always. But there is a problem definition part, which is what correlation is the AI algorithm trying to find? That has to come from the domain. So the domain expert has to tell it, well, this is ice cream and this is sunset. And you want to find a correlation between the two. So that is sort of the problem definition statement. We'll come to that as well later. So yeah, so as I was saying, what the AI algorithm does is it finds this correlation by looking, and just like a toddler looks or experiences, right? So what does the AI algorithm do? It looks at lots and lots of pairs of these variables, independent and dependent variables. So
Sorry
yes,
to interrupt you, but Aditya has a question.
sorry. Yes, I can't see the hands, unfortunately. So if you can just go one by one, and Joanna, if you can just mediate the
So
order.
he has asked
Yeah.
on the chat, what is the difference between features and labels?
I'm going to talk about that in a second. Yeah. Are there other questions?
That's it. You can go
Okay.
ahead, Arpan, thanks.
Yeah. So what the AI algorithm does is it looks at lots and lots of pairs of variables like this. So what is a pair? So the ice cream and sunset is a pair, for example, right? Time at which given ice cream is part of the data. It's part of this pair. Right? The sunset is the label because that's what the toddler is trying to predict. So the independent variables are the features, the dependent variables are the labels. So the outcome that the AI is trying to predict is called the label. The input data that goes into the prediction is called the set of features. So going back to the toddler example, um, the act of giving ice cream to the toddler is the feature, and that feature is either the ice cream is given or the ice cream is not given, right? And the existence of the sunset is the label. So based on the toddler getting the ice cream, she or not, she predicts whether the sun is setting. But it's not really a prediction; it's a discovery of a correlation. Right? So this collection of pairs, where features are the input data, labels are the output of the AI algorithm. This collection of pairs of features and labels is called label data. And the method of looking, the method of discovering this correlation is called the training algorithm for the AI. So you're training the AI to discover a certain correlation. And that's why it's called the training algorithm. So all of these names, right, like training the AI, these names give it the illusion of intelligence, but really there's no intelligence. It's just a correlation discovery algorithm in a sense. And there are many different types, mathematically from the computer science perspective, there are many different types of training algorithms. And so, when you give a problem to the AML team and they say they are experimenting with things, what are they doing? They are sort of experimenting with different types of training algorithms to see which one works best. And again, I'll make all of this concrete. What do we mean by works best and so on? Okay.
Alpan, a couple of questions. One I think you've answered, but one came from Aditya. What is the difference between features and labels? I assume, Aditya, you can just respond on the chat that that's been answered, but if it is not, please speak.
Yes, Aditya, please. If it's not clear, let me know.
It's clear. Thank you.
Okay. And Arun has asked, Alpan, within the context of AI, could you elaborate on when correlation can be said to be justifiably implied causation? Wow, this is my kind of question. Okay.
Good question. I was hoping someone.
I always have an argument with Alpan on causation. Please answer that, Alpan.
So correlation never implies causation, right? And there are a special set of.
Can you define those two terms and explain them with examples, please?
Yes. So, so let me start with the classic example, and that is global warming. We all of us know that the temperature of the Earth has been steadily increasing. The average temperature over a year has been steadily increasing. The other thing that we know is that piracy in the high seas has been going down. So, so if I were an AI algorithm and I'm only looking at pirates and I'm only monitoring the temperature of the Earth, I would say there's a correlation. Piracy goes down, temperature goes up. So how do I cool the Earth down? I increase the number of pirates. I start doing piracy on the high seas. Would this be a correct conclusion? No. Because there is no causative relationship between piracy and global warming. It's simple coincidence. It's just time. With time, we've gotten better at catching pirates, and with time, we've made the world more polluted. Right? So that's a correlation. Most AI algorithms, what they do, and that's why one has to be very careful in applying AI. We have to be very careful because what most AI algorithms do is discover this correlation. They don't discover root causes behind the effect. There are a separate set of models that that sort of do causality analysis, but they're fairly complicated. I don't want to get into the technical issues here. But for the most part, all AI is doing is discovering these correlations. And the hope is that if you give the AI enough data, then these correlations are real. They're actually real effects. They don't correspond to something like piracy and global warming. But an AI algorithm never finds a root cause of something. It only finds a correlation. So it's really not intelligent. Right? It's pretty dumb. Yeah.
So Alpan, is it okay? Is it okay for our models? Because finally we look at its performance, etc.
Yeah.
As long as the correlation is extremely strong, but we are not so sure, not to be understand at some level the causality. Is that an acceptable thing, or is it a cause of concern? How should we think about this?
It can be a cause of concern, and especially when you try and attribute, when you try to do attribution. So, for example, often in medical applications, we want to know why has the AI predicted this, and we say, well, these features, take certain values, and therefore the AI has predicted this. We call this interpretation of the AI algorithm, right? Again, this should be taken with a pinch of salt. It doesn't mean that there is a causative relationship. So in other words, if the AI method has value in terms of the accuracy of the prediction, in terms of the how should I put it? In terms of the its ability to discover the correlation or uncover the correlation. If it has value, if that part has value, then it's worth deploying an AI algorithm. But if you're really looking for root causes, AI is probably not the best choice.
Understood. Nakul had a question.
Yes, Nakul.
Yeah.
Sorry, I was just typing it down. So yeah. So Alpan, wouldn't it mean that in a good AI model inherently has causation behind the correlation? It's just that we cannot uncover what the causation is. Because you mentioned that the pirate example that you gave, that it could be a coincidence.
Yeah.
We wouldn't want to base our results if the correlation does not have a causation behind it.
Yeah. So this is why evaluation is extremely important. So now, if you, let's say you blindly accepted this AI algorithm where from pirate data, it is predicting the temperature of the earth. Let's say you have an algorithm like this. It all looks very good. You've tested it in the lab. Now you deploy it, meaning you start using it to actually predict the temperature of the earth. One fine year, there's a lot of pirates, but the temperature still goes up. The AI model has made an error. So in deployment, you will discover these errors. And then you have to go back and say, what did I do wrong? So in other words, if you continuously keep evaluating the AI model, if you give it a lot of data from a diverse set of instances, you hope that these spurious effects, these spurious correlations will actually go away. And you will actually have something that is causative. But fundamentally, mathematically, what it is doing in the back end is just discovering a correlation.
And Alpan, on the example that you gave, you actually gave the answer. At least I saw an answer in that. You said about pirates and global warming, but there is a underlying causal variable which was not offered, which is time.
Time, exactly. So there could be an additional.
Right. So to a certain extent, the AI algorithm could only solve it, but actually it was not doing too bad a job because the underlying core variable which it did not track to as a feature may have been time.
Yes.
So it's so in a different way, we can say that some of these could be because there are other factors that are represented using these features that is causing the AI algorithm to come to a fairly decent conclusion.
Exactly, which is why, when I know program folks are often very, very frustrated by this. And we saw this in, for example, the LFU, in the LFU prediction project, where the CTD kept asking us, what data do you need in order to predict LFU? Right? And the AI team is always worried that, if they take a subset of the data, just a few registers or a few columns, then they may be missing factors that are important and they will end up discovering these spurious correlations. So the AIML team always tells you, no, give us all the data that you have. And then it becomes a frustrating back and forth. But, independent of what is practically feasible, the reason why they're asking for all the data is because they want to eliminate these spurious correlations.
Alpan, 4 more questions, so we'll just be on the slide.
Sure.
Malay asks if we can't decide causality.
Yeah.
So if we can't decide causality, how do we assign some variables as labels and others as features?
Okay, that's a good question. This is exactly like doing linear regression. You're familiar with linear regression, right?
Right.
Yeah. So in linear regression, you don't discover causality. You have a dependent variable and you have a set of independent variables, and you predict the dependent variable from the independent variables. Now, who decides which should be the dependent variable and which should be the independent variables? It is decided on the basis of the problem that has to be solved. So it comes from the domain. The domain defines what is it that you want to predict. If I'm trying to find TB from cough sounds, it's the domain that has said, look at the cough sound and find this disease called TB. Don't find something else. Maybe there is a signal for something else also in the cough sounds. So then the existence of TB becomes the dependent variable. The features in the cough sounds, all the different sound patterns, become the independent variables.
And Alpan,
Understood.
I want to add to what you said. You can make a converse problem. You can say I want to detect noise pollution in a house by the amount of coughing that is taking place. And in that case, the TB becomes a feature. And the extent of cough may become or the level of noise pollution may become the label, isn't it? So it depends on what you're solving.
Yes. So it completely depends on how you define the problem in the first place.
So the same problem could have it as one is independent, one is dependent, because of correlation, they probably tend to occur in some manner, but it depends on what problem you're solving.
Yes.
Very good. Ayushi is asking,
Yes.
how can one identify correlations that may be a pure coincidence? And is there a way to tell the model to ignore this?
Very, very good question. Very good question. So Ayushi, this is where the large amount of data comes in. If the AI is given five data points, meaning 5 sets of features and labels, there could be a correlation between these, within this very limited set of data that is spurious. That's just a coincidence, as you rightly point out. But if I give you 100,000 data points or 100,000 set of pairs of features and labels, and the correlation persists through this set of 100,000 data points, it's probably not a coincidence. And that's why, AI algorithms rely on large amounts of data. This is number one. Number two, even among large sets of data, there could be spurious correlations, especially if the data is biased. And we'll come to this a little bit later. So for example, if you've taken all your 100,000 examples from, say, the population of Madagascar, small country, and then you don't know anything about, let's say I give you an AI model. Again, I'm sort of jumping the gun here because I haven't told you about stuff like this, but I'm going to risk it anyway. Suppose I've made an AI model based on data from Madagascar and I'm trying to apply it to India. It will start making mistakes because it's discovered correlations, perhaps, that may have existed in Madagascar, but the correlation is completely absent in India. So for example, in Madagascar, maybe it's the case that there is a correlation between stunting and a certain disease. That correlation is completely absent in India. The AI model will fail spectacularly in India. And from that failure, we'll then question what we did in the first place. Ideally, we shouldn't have to reach that point in order to question what we did in the first place. Just by knowing the fact that the data was all collected from one location, we should be able to say that there is something wrong. You have a high chance of getting coincidental correlations or biases in the data, as we call them, because you took all the data from a very, very limited setting. Does that answer the question?
Yes, Alpan, just to clarify, what you're saying is that you can't really go ahead and keep looking for all these coincidental correlations. What you can do is avoid it upfront by collecting unbiased data, large amounts of data, etc.
Exactly.
And let's say you happen to find something. Okay, you happen to find that for some reason it's has learned something that's not very accurate or not very good. There's no way to tell it to ignore it. You just have to feed it better data.
No, there are ways. There are sophisticated ways.
Okay.
And I'll give you an example of the Anthro project, right?
Yes.
There was this thing happened, which we hadn't anticipated. So we found, what did we find? In the hospital setting, Makarand and his team found that
The bed borderline.
even without a reference object, they could infer the weight very accurately. And that's because there was a hidden reference object defined by the boundary of the bed or the bed sheet, right? And you know that hidden reference object would not exist in the real world. So it's discovered a coincidental correlation and said, okay, this boundary of the bed sheet tells me the depth. That's what the AI algorithm has discovered. And because of the depth, now I can estimate the weight really well. So the AI model, again, is not intelligent. It's discovering any correlation it can between the features and the labels. It will exploit anything within the data in order to be able to predict the labels accurately. It's like this bot that's exploiting correlations. That's why we have to be very careful with data issues in AI models. Yeah.
Alpan, there's one more question and one request from this
Yeah.
request is from me.
Yeah.
Alpan, because what you are saying, and there's a lot of content.
Yes,
may
yes. It
request
comes
you
up
to-
later.
Yeah, no. I request you to give a slightly elongated pause after you say something, because I want
Sure.
everybody to get some time to just,
Sure.
mentally
Let it
process.
sink in.
Yeah,
Yes,
it'll
yes.
take some time because,
Absolutely.
it's not
Yes.
that easy. Everything you say is not that easy. So
I
let's
know.
just mull, even if it's 5, 10, 15, 20 seconds, I think that's well worth for people to just, mull over things. Another question in the meanwhile, JK is asking this. In statistics, p-value of less than 0.05 is defined as significant.
Yes.
Is there a threshold for the metric of correlation? What and how much?
No. In fact, the AI doesn't explicitly compute a correlation at all. It the various. So JK, you're asking this question from a statistics background, where one is taught correlation coefficients, things like linear correlation coefficients, some non-parametric correlation coefficients, and so on. The correlations that are discovered by an AI model are so highly nonlinear that they can't be captured by a simple number like a correlation coefficient. And the significance of that correlation cannot be captured by a p-value.
Alpan, Mihir asks,
Yes.
is it accurate to say if there are variables in the data set that are known from domain knowledge to influence the outcome, it is likelier that the correlations discovered is not spurious. That is most
Correct.
likely encode some sort of causation.
Correct.
It
Very
is
important.
a mouthful, but can you decipher it?
Yes. So let me explain the question to the rest of the team. So what Mihir is asking is, suppose we knew from domain knowledge. So if I had, again, going back to my pirate and Earth temperature example, I am this dumb guy who has no idea that piracy should not be correlated with Earth temperature. I'm just this dumb guy coming from IIT or a school like this and doing coding, right? I have no knowledge of the outside world like most IITians, and all I do is code, right? I have no idea about anything else. Then I have a weather expert who comes and tells me that what the hell are you doing? Why are you coding features for piracy in order to predict weather, in order to predict temperature? It doesn't make sense. There is no, piracy has nothing to do with the weather. And I look at him dumbly and say, really? And he says, yeah, in fact, what you should be looking at are things like, maybe you should be if you want to predict temperature, you should be maybe looking at wind speeds. You should be looking at season data. What season are you in? You should be looking at latitude and longitude. These should be your features if you want to predict temperature. Just throw away that piracy feature. And so I have an example where a domain expert has come in and said, here are the features to look at. Right? That is the ideal scenario. If a domain expert can tell us, look, these are the most important features that will result in your outcome, then those features should be explicitly included in the model. That data corresponding to those features should be included while training the model, so that there is a high chance that you discover a spurious or a coincidental correlation. Because the domain expert knows that there is a causative relationship between those features, namely latitude, longitude, season data, things like that, and the temperature.
And Alpan, I will add one real life example, I think, which is there in adherence. So in adherence, we are trying to predict whether a patient, TB patient, will adhere to the medication.
Yes.
And so the expected set of features that people brought to the table were, their sex, male, female, transgender, because we know there may be a high amount in transgender communities, poverty levels, maybe some aspects of their own other health signals.
Yes.
But the discovery that occurred through the AI model brought a feature that was high ranking in terms of uh, its its participation, if you will, in driving the outcome, and that was whether a person had a bank account or not. Now,
Yes.
this is not so obvious for us. So, as
Yes.
human beings, we may not have intuitively thought about it, but
Yes.
if we sit down a little and think a little harder, maybe we will start creating some linkages as to why
Yes.
it signals something. Maybe it signals a level of poverty, maybe it signals a level of literacy, maybe it signals a level of willingness to work with the world at large, to reach out to communities, maybe a institution like a bank. We can
Yeah, or it could
rationalize
be,
this.
yeah, exactly. Or it could be simply that if you don't have a bank account, then it's a signal of the fact that you have your economic status is low, and therefore you are under a high degree of stress. You're constantly looking for jobs and so on. You don't have time to worry about vacation, taking it.
Correct. Correct. And another maybe interesting feature we can think of is the availability for an individual of a BPL card, because that also is one
Yes.
that may be interesting. That's a different.
Yes, similar. Yeah.
Yeah. Shivi Kapil asks an excellent question, which is how do we ensure that we have enough labels and a set of features to correlate something? Is this an evolving process? If so, when do we stop before deployment? What is
Correct.
the amount that you need to do?
Good question. There's no universal answer to this. The short answer is, sorry. The short answer is we never fully know whether we've exhausted the set of features. That's why, and if you talk to an AIML person, they will always say, give us all the data that you have, right? Don't exclude anything. Because we'll never know what set of features is exhaustive for the label in question. We typically will deploy a model when we realize through our own internal experimentation that it has sufficient accuracy in predicting the label in a sufficiently diverse set of circumstances. And again, as we progress through this presentation, these things will become clear what I mean by sufficient accuracy, sufficiently diverse set, and so on.
All right.
But it's a judgment call.
Thanks, Alpan.
Again, just to keep it very centric on our training session, the reason I started participating is I wanted to provoke questions. And
Yes.
for me, asking questions has a very strong causality and correlation to learning.
Yes.
Because
Great.
the only time you learn is when you ask.
Yes. And that's why, please, everybody, please don't shy away from asking questions.
Right. There are more questions.
Great.
So, Alpan, you'll
Yes.
get through 2.5 slides per session.
That's great. I don't mind doing 20 sessions, by the way. We'll go through this slowly. Yeah.
Very good. How do we check the quality of data before using it? Malay asks.
Yes.
You can cite example of Nikshay data, it will help, apart from missing values.
Apart from missing values. Yeah. So there are basic, again, we're a little bit jumping the gun, but I'm going to answer this anyway. There's a later slide on data quality and so on. There are various aspects to data quality, right? Missing values is one aspect. That's an obvious aspect. The other is values that are simply wrong. So if you have, remember that the AI is trying to exploit correlations. Now, you don't want the AI to come up with a spurious or coincidental correlation. And if your data is wrong, it may find a correlation between that wrong data and the label, right? So for example, if your age values in the data are wrong, you have people who are 200 years old or 300 years old, or 1-year-olds in Nikshay who have TB or something like that. That causes a huge problem for the AI because it can potentially start correlating this wrong data to the label. Right? So this is one data quality issue. We have to ensure that all the values are accurate. Right? So accuracy and quality go hand in hand. This also applies to the labels. So let's say your label is whether, if you're predicting adherence, for example, your label could be whether the patient went LFU, meaning the patient completed their treatment or not. Now you need accurate labels. If that If that is wrong, if the patient actually completed the treatment but is listed in Dikshay as the patient did not complete the treatment, that's a problem, because again that will lead to you should just think of the AI as this dumb system that discovers correlations. The moment you have an error in data, it can exploit the error and discover a incorrect correlation.
And I'll add one piece. Later, we'll be going over internally as well other aspects which are
Yes.
external to the system. I'll probably take that course after Alban finishes this on the maturity model, which addresses this in a lot of detail, Malay. But hopefully, you've got a good sense of what Alban is speaking
then
about.
these are some of the obviously wrong aspects, bad aspects to data. The other aspects could just be bias, right? Suppose all the data that you give me was collected by a single operator. Then there could be hidden biases that I don't even know about. And that will cause the AI model to fail in deployment. A different operator is using the model.
And I'll give you an example that Alpan beautifully explained to me about a year and a half ago. So we had originally only two nurses, two ladies within Nilofer Hospital who were taking the video of the baby. So these two ladies would come in and take the video of the baby. And we used the model to train it. Alpan made an astute observation saying that the model is probably learning the movement of their hands. It's a very important statement, because what it says is if the model just gets two people, they probably have a habit of taking a photo or a video in a certain manner. Accidentally, the manner in which they take the video becomes the feature.
Yes.
Rather than the baby in it. And so the feature, AI doesn't care about all this. Assume that it gets the sequence of images in a certain manner, or it gets in a certain situation. By mistake, it really doesn't know how to distinguish anything. So anything you provide into AI appears accidentally or otherwise, you have to be doubly, triply careful of introducing unintended errors into the process. This is what I learned when he said that.
So an extreme example of that, just to make it more concrete, suppose you have two nurses collecting the data for you. One is a short nurse and one is a tall nurse. So one nurse is always close to the baby. One nurse is always far away from the baby, relatively. Suppose just by coincidence, and you never planned for this, but coincidences can happen. So, certain things can happen in the field. Just by coincidence, the short nurse tends to take more videos of underweight babies, and the tall nurse tends to take more videos of normal babies. Then the AI algorithm that is trained on that data is going to be very, very high accuracy, with very high accuracy, going to be able to predict whether your baby is underweight or normal. Why? Because every time it sees a baby that is close, because the short nurse has taken the data, it will predict underweight. It will learn to discover that it has found a spurious correlation in the data. Namely, if the baby is filling the frame because of the underweight nurse, because of the short nurse, then it's an underweight baby. While if the baby is not filling the frame because the picture has been taken by a tall nurse, then it's a normal baby. This is the correlation that the AI discovers. It's a spurious, it's a wrong correlation, but it's discovered it and therefore happens to do very well on this data set, but will not do well when you deploy it in the real world, because there are all kinds of nurses and all kinds of people taking data in the real world. So these are the things to be careful about.
And to the same point, to more, sorry, go ahead.
Okay, so in in the data system like Nikshay, there are thousands of NTEP staff who conduct this data entry.
Correct.
So what would be the scenario in that aspect? This is totally opposite to what you have cited, two nurses.
Yes. So there the problem may not be the data operator. The problem could be of different types. Suppose I'm using an AI model that is trained on Nikshay data that was gathered during the height of the COVID wave. And now COVID is largely over. I'm applying the algorithm. I find that the algorithm fails spectacularly, even though it did very well on my test set. Now, why is that? Maybe there is something different happening to the patients during the COVID wave. right? And we didn't look at the dates. We didn't look at when this data was collected. There could be hidden biases in the data because it was collected during a very unusual period in our history.
Also, to add on to what Alpan said, Malay, often data quality rigor, if we employ, a lot of the data, let's assume you have 100,000 patients' data, maybe 80,000 or even 90,000 will get discarded for one reason or the other. So this is an art form. There is a counterpoint to this, which is that even if there is, we call these problems in data, we often call it noise. So even if there is some noise in data, as long as you get large enough data, some of that noise does not play an effect. But this whole concept of data quality has a lot to do with downstream, which is how good are your operational systems? What's the validation checks that is taking place? So if you have a system correlated checks, so you've got formal checks, which is, if it's a date, it must contain a date. A lot of dates contain 00 and all. That's not the case. Likewise, you must have accurate information. If there's male, female, and transgender, which is MF and X, say, and then if you have a W there, you don't know how to interpret it. Or you can have a male human being, it's a male, and we have information saying that person has delivered 4 babies. So that's wrong. It's a correlation logic check. So there could be various aspects of data quality in of itself a fairly rich aspect, which actually, once more, in my humble observation, falls on the domain. Domain should be able to have some generic rules, which right up front, as soon as you see data, you should be able to make these assertions, what I call assertions. You should be able to say, in this data set, we in general expect data to look like this. And that helps a lot. Alpan, going back one more question, Nakul.
Sure.
It will also, wait, I will not be able to read. Nakul, can you read? My eyesight is not.
Yeah, Nakul, can you just speak up? Yeah.
Yeah, so not really a question, but I know you're going to cover regression versus correlation versus causation later on. But if not, it'll be good if we can just talk about how they're different, because we use these terms, but yeah, a lot of us might not be aware.
I won't cover causation as such. I mean, most AI methods actually don't uncover causation, so I'm not going to go into it in this lecture. Regression is really a model. I'll talk about regression a little bit later, so you don't have to worry about it right now. But for now, just think of an AI system as uncovering correlations. Even regression is a type of regression analysis also uncovers correlations.
Aditya asks, extension to JK's question, if we cannot quantify correlations, how do we explain the difference?
Explain the difference between?
Sorry, explain the inference. Sorry.
Yeah, explainability is one of the limitations of AI models. If your system requires a high level of explainability, the first question you should ask is, should I use AI? Explainability is in some sense a somewhat artificial construct when it comes to AI. Simple systems or simple models are explainable. AI models being extremely complex because they're trying to discover all these hidden correlations tend to be very, very complex. The negative aspect or the disadvantage of AI models is typically they have a low degree of explainability. If you ask why did the AI did this, usually the AI scientist is going to groan and say, oh my God, do I actually have to explain this? Because it is very difficult, and it's very difficult to find a consistent explanation. There are, various methods of doing, in some sense, explainability in AI systems, and often all these different technical methods give you different results. So then, if they give you different results, you haven't really explained it.
So, Alpan, that was helpful. Just as a follow-on, so when you said, for example, in our Anthro project, we found out that the algorithm was looking at the bed sheet as the reference object. So
yes. How did we find?
Yeah, is that through like some kind of mathematical sort of?
No, so it's a combination of two things. So there are some approximate in computer vision AI, and again, this is in the very specific case of computer vision AI. There are some methods where, again, this is getting into more detail than I'd like to at this point, but anyway, in computer vision AI, you typically use neural network models, and there are ways of telling um, which part of the image is the neural network focusing on more. There are other mechanisms called attention mechanisms as well that tell you similar things, but there's a way of telling which part of the image is it focusing on more. So that can tell you where is the neural network or the AI looking, in a sense, what part of the image. So that can give you some information. The other is you do a lot of elimination type experiments where you say, okay, if I remove this background, if I remove the white sheet, then does it do as well? And you suddenly see that it doesn't do as well, right? Things like that. So by having counterfactuals, by actually removing parts of the image, you look at what happens to the accuracy of the model. And based on that, you infer, it must be the white sheet that is doing this.
And
does that answer your question?
Yes.
Okay.
One request, please don't ask any more questions. We'll just finish the set that I have, about 3 more. And we'll go over session by about 3-4 minutes. And
sure.
Then, you know,
let me, I think maybe I can finish this one slide.
Yes.
Yeah.
Should we go ahead with the questions, Alpan, or no? Right away or no?
Let me just finish this slide. I just have one more point to make, and then we can address all the questions together.
Sure.
Yeah. So, so the third point I was making here is that the AI algorithm finds this correlation between features and labels. And the method of finding it is called the training algorithm for the AI. So if somebody says they're training an AI model, then that's what they're doing, is they're writing code that discovers this correlation. And then they have to run this code. In some AI models, it takes a long time to run the code. The code can run over days. For days, it's doing stuff to find this correlation, right? Now, once the AI has finished this looking or training process, looking at the data, then it creates what we call a model of the correlation found, right? And this model is some complex mathematical thing. It's not a single correlation coefficient as you are used to in statistics. It's a very complicated model that, what is the function of this model? Well, if you give it new features, a set of features, it will predict a label. That's all the model does, right? And this model is what we call an AI model and is ready to be used or deployed in the field. So this process of using the AI in the field or deploying it, meaning giving it features as an input and the AI model predicting a label, this process is called inference, right? So inference is the process of exploiting the correlations that it learned during the training phase. Okay. So during inference, as I've said before, the AI model is fed with features. And going back to the toddler example, feature could be ice cream versus no ice cream. And it predicts the outcome of the label, which is sunset or no sunset in this example. Okay, I'm going to pause there and let's take all the remaining questions.
Right. JK asks 2 questions, I think one of which is going to be a little later, but anyway, you can answer it. Could you please contrast explainability versus causality?
That's a good question. So if you have a causal process, then that's stronger than explainability in a sense. So if you know the cause, then that cause is the explanation, in other words. So there's no distinction. There are certain cases where you can discover the parts of the model that are leading to, the features that are leading to the outcome, but you may not still know the root cause. The root cause could still lie outside the features, right? So for example, let me think of a good example. So the pirate example. Suppose an additional feature was time. Now, time is not really the root cause. It's the things that have happened with time, right? With time, what has happened? People have polluted the world more because of industrialization. So the root cause is really industrialization behind global warming, right? And policing systems have gotten better with time, and therefore there is less piracy. right? So the root cause of piracy going down is really improvement in policing systems, but that is not part of the data. So I may have discovered an explanation and said time is the explanation. That's not the root cause. That's where the distinction lies. If you can discover root cause, that's the real explanation. But you can often discover explanations within the data that are not the root cause. The root cause lies somewhere else.
Very well said. Very well said, Alpan. JK asks, Alpan, is it possible to encounter scenarios for an outcome where published literature suggests a positive correlation for a specific feature, while AI model is suggesting a negative inverse correlation for the same feature? And if so, which overrides the other?
There's no universal answer to that question. So say published literature says, there's a positive correlation. You have to go back and look at the data. In other words, on what, basis what data has published literature said this? Are they looking to buy a set of data? Conversely, has the AI looked at a very different data set and found a negative correlation? So that's the first question you'd have to investigate this further. You can't say sweepingly that one of them is right or wrong. You'd really have to look at, what is the data on the basis of which these conclusions were made. Now, suppose it's the same data on the basis of which both the conclusions were made, then you really have to investigate further. What is the difference? Like, why is published literature saying what it is? Why is the AI doing what it is? Has the AI found a spurious correlation? On the other hand, has the published literature ignored certain factors on the ground that the AI has incorporated? You really have to dig into details. There's no universal answer.
Thanks, sir.
Shekhar Vaikar asks, what are the criteria to see there is enough data for an AI solution?
I'll come to that. We'll slowly come to that. Yeah.
Sure. And Vichi says, is it fair to say that because there could be a large number of variables that affect outcome, some known and some unknown, we need to have a large data set to counter effects of spurious correlations and biases creeping in?
So the second part is certainly true, that having large data sets helps. Helps in terms of removing spurious correlations. But the known unknown part is not exactly related to that. So even if all the correlations are known, just the fact that you have a small data set could by itself lead to spurious correlations. Does that answer, or are you really asking something else? Not clear.
That makes sense, Vijay says. Ria asks, is there a specific timeline to get our output? That is a successful model of correlation, or is this a continuous process of feeding data?
The correct answer is continuous process. Now, practically, we can't keep doing this for infinite time. Right? So we have to stop somewhere. And we usually stop when the accuracy, and part of this training will involve talking about accuracy later on. But we typically stop when the accuracy reaches a certain level in many different kinds of tests that we do. So, but the moment the accuracy dips, then you have to often feed it more data, more fresh data, because the nature of the correlation could have changed with time.
Okay, so is it a long script that keeps running for hours, or how is it?
It could even be a short script that keeps running for hours. I mean, basically, if you have, so how best
I'll
I
answer.
describe it?
I'll answer
Yes.
that.
Sure.
Yeah, Ria, I think we've got a set of data. Let's say there's 100,000 rows of data. So the way it works is typically the algorithm will run fully 100,000 in its time, however much time it takes. The larger context is, as we go into production, we've only had 100,000. Now new data will start coming in, and we'll get another 10,000, 15,000, 20,000. So Alpan's point is, as we go to deployment, and as we get more and more data, that means instead of 100,000, 1 lakh, you now have 3 lakh data. Now you go back and take the entire 3 lakhs, and maybe you retrain the model again with the 3 lakh data. So it's at one instance, you just process the data once, but the concept of continual is not incomplete processing of input. It is continuously getting new input because we are constantly increasing the number of inferences, the amount of deployment, the amount of data you are collecting. That is a continuous process. That's what is.
Yeah, there's another aspect to it, which is even with a fixed amount of data, the AI, the training algorithm can take a long time to run, and that is because this the way the AI finds correlations is through what is known as a parameterized model. It's a model. It's a set of numbers or a set of variables called parameters, and it finds the correlations by finding the right values of these parameters. And to find the right value, it has to do a lot of exploration. If you have like 100,000 parameters, then it keeps checking different values of these parameters and asks, okay, with these values of parameters, have I found the correlation? No. Then let me fiddle the values a little bit more. Now do I get a better correlation? Yes. So now let me fiddle a little bit more. This process of keeping, fiddling around with the parameters takes a long time. So that is the process of training.
Got it. Thank you.
I think, JK asks, is there a way to make the AI model predictions immune to under-reporting or improved reporting or over-reporting of outcomes of interest?
I don't quite understand the question. What do you mean immune to under-reporting and?
Alpan, sometimes, example, a COVID scenario.
Yeah.
The outcome of interest actually could have happened in the field, but people did not report it at the desired optimum level. Or it can be a converse scenario. It can lead to improved health-seeking behavior, and even the cases which are likely to be missed pre-COVID were filtered out. With
No, but what is the AI predicting?
That specific outcome of interest, the model's performance.
Yeah, so all you're saying is you don't have enough data to predict the outcome, right? Under-reporting means you don't have enough data, or you have less data. Over-reporting means you have a lot of data. Is that what you're saying?
I'll recall an example. In 2019 data, models have demonstrated a certain level of performance, and in 2020 data, which was against the pandemic backdrop, we expected actually an increase in LFU rate, but the LFU rate in the program diminished. The common sense and the programmatic knowledge, inclined to increase in LFU rates in the COVID times, but something contrary happened to that, and
because it was not being reported. No, so there are two things. One is, did the model predict a decreased LFU rate, or was there actually a decreased LFU rate?
There was actually a reported decrease in the LFU rate from the program.
And what did the model predict?
The model predict fairly equally. How do we adjust
for that? Yes, because the model was trained on data from earlier. So then the question you ask is, so there is a discrepancy between what the model has predicted and what actually happened, which is what we call error, right? But now you have, again, this is a case-by-case investigation. Why is there a discrepancy is the natural question. Is it because the AI model didn't discover the correlations correctly, meaning is it a bad model? Or is it because the data was, there was missing data? And if the data had been correctly reported, then the AI model would have been right. So you have to ask which one is it?
Understood. So extension to this, there was this reference of if our models were originally trained on Nikshay data, which had some quality issues, if we are given more sanctified, validated data, is it natural to assume that our models will showcase better performance given?
Yes, all other things being equal, the performance should improve.
Oh,
yes.
Thanks, Alpan. Thanks.
Yeah.
So Alpan, I think we have gone over time, but that's fine. So a couple of learning, maybe Alpan, you need to plan about 40 or 45 minutes only, because as expected, it takes a little bit of time for people to start thinking and asking questions. So
yes,
we need to keep a clean 15 minutes at the end, 15 to 20 minutes for people to really, reflect and start asking questions.
Yes.
Based on their experience.
Yes, so it is going to take a while to get through this. I can see that. That's
right.
fine.
It is. And the other piece, Again, first, thanks, Alpan. I think it's very useful. And I think everybody, maybe we can open a small channel in our Slack channel.
Yes.
Call it Alpan's trainings or Alpan's whatever.
Yeah, just call it training, ML training.
Okay, ML training. And everybody can start asking questions there. And I would strongly encourage, it's the first time we're doing it. And so some people, their nature is such, they will tend to ask more questions. But it's super important. I think Alpan barely got through 4 slides, but Alpan will share it. I'm sure he'll put it there. Go over the 4 or 5 slides that he has gone through. And my only suggestion in order to make sure that we prepare ourselves well is go over it in thorough detail. Make sure you understand it thoroughly. And I would encourage even dialogue within the organization. You need not come to Alpan alone. You can also probably have dialogue with one another. Of course, if you have a doubt, a material doubt, it's useful to go to Alpan. You can post questions in that channel. I will highly encourage that because I think either Alpan will answer it at that time, but even if he doesn't, then Alpan, you need not feel obligated that everything you need to answer immediately. But before the next session or some important questions, like this, because this learning process is Alpan often says it's not what he says, it's what you listen and process. So what he said,
what I'm saying is not important. What is actually absorbed is important. So emission is not important, it's the absorption.
So it's super important. And some of the simple indicators of absorptions are questions and level of question and dialogue. And over a period of time, we hope, because the material will get more detailed and more specific. So you need to get your fundamental grounding so that you don't have doubts when we go into, more complicated material. You should not have doubts in the early material. Otherwise, you will struggle, and not only struggle, 2 things are guaranteed to happen if that happens. 1, you will struggle. 2, you will lose interest. 3, you will stop learning. This is the sequence. If you look at anybody who has studied anything in their life, the time you stop learning is when you go past a word you have not understood. And if you do that, you start developing dislike for the subject. In fact, it's the other way around. When people learn something well, they're learning. There's a huge question I have. Does intent cause action or does action cause intent? So if I become good in something, because I become good at something, does that cause me to have a huge intent with it? Or am I so good that I think I want to do something and I get to it? Actually, it's an interesting philosophical question. I'll leave you to ponder with that. As it applies to this session, I want all of you to really think deeply and write down notes, write down questions, make sure this is crystal clear in your mind. Because I know I'm not seeing the material, I know the way Alpan teaches, it's just starting to, over time, it'll just start to get a little more active, a little more hectic with the material. And at that time, it's useful for you to have clear fundamentals. Alpan, that does make sense, no?
Yes. So what I'll do is I'll actually share the part of the presentation that part of the deck that I presented so far, along with the glossary of terms. I'll just put it on the Slack channel. So if somebody, Joanna, can you create a Slack channel, like an ML learning or something, ML training or something, and I'll just upload the deck to that channel. And it's just that everybody here will have to be added.
One last question. Sorry, Alpan, I missed out. Vikram asked, is bias in data always wrong? Can we have cases where bias can achieve great results while we make adjustments in program and deployment?
So it's not about right and wrong, Vikram. If there is bias in the real world, that bias is to be reflected in the data, right? Because if you really want the AI to do well in the real world, now this is a controversial issue, right? Do you really want the AI to reflect the real world? Now, when you look at, for example, these large-scale NLP systems that actually amplify biases that in fact exist in the real world, right? So the question is, do you want to change the data that is fed to the AI in a way that you reduce those biases? or do you want it to actually reflect those biases? And this is very, very context dependent. In the case of some of these sort of captioning systems or NLP, large scale NLP systems, biases have become a huge ethical issue. In the space in which we work, not sure. In some cases, it may be a huge issue where you actually want to change the data in order for the AI not to have certain biases. In certain cases, you actually may want to reflect the actual bias on the ground. And again, we will be discussing some of these things.
Very good. I think we are done. Thanks, Alpan. Thank you very much. Again, once we create the channel, just from a timeline perspective, it's going to take about a couple of months or 3 for everybody to be comfortable and thoroughly comfortable. And that's going to be an important milestone for our institute. Just make sure that the level of AI awareness, knowledge, vocabulary, talking, discussing with third party goes to another level. This is a critical goal for our institute in the short term. And so again, thank you, Alpan, for taking the lead.
Yeah, and also one more thing, if people are comfortable with it, is it okay for me to do 2 sessions per week, 1 hour, 2 1-hour sessions per week?
Yes. Just go ahead and do it. This is more important than, if you will, most other meetings that we have. So folks just can sort themselves out. Joanna just work out schedules that make sense, but let's just get through it. But it also requires, I think, for every hour of learning, or every hour that Alpan disseminates knowledge, I would argue you need about a couple of hours of introspection, writing, understanding. So if he does 2 hours, you can assume you need another 4 to 5 hours in a week to make sure these concepts go in thoroughly. Once more, just for what Alpan said at the beginning, once we get through this and people are comfortable, and it will take some time, but the goal is for us as an institute to reach the next level. Don't forget that goal that we have. Thanks, Alpan. Thank you.
Thank you.
Thanks. Take care. Bye.